Hi, we recently purchased a small desktop laser for our latex business. We use it to cut shapes in latex, which is a rubber, as you know, and it's very good for that. The one we bought is the one on the screen, which is which is a diode laser, what's called a diode laser. And I started looking at this because obviously the laser safety side of it is pretty important. These things are potentially very dangerous. Now, I studied lasers at university in my final year. I'm a mechanical engineer, but it's been a long time, so I had to go back and have a look at all this stuff again. So I put together this document, which I'll go through the basics of it. Some of it relates to specifically to cutting latex, which obviously is not really that important to what I'm doing here. But I just thought I'd go through it because the same questions do get asked quite a bit on various laser groups that I'm on. Right, so the first thing I think we probably need to do, incidentally, if there's anything wrong here, if I've misunderstood stuff myself, please let me know, and I'm more than happy to update the video, do another one, whatever. Okay, I'm not professing to be an expert in lasers. I'm certainly not. As I say, I'm a mechanical engineer, not a physicist. Although obviously physics is part of a mechanical engineering degree. Right, anyway, the first thing I think we should look at is what really is colour. What is colour? Right, and you might think, well, that's a bit of a weird question, but bear with me, it will become obvious, the importance of it, hopefully. So this little diagram here that I've got shows a blue object. This thing here down the bottom is blue. Well, what does that really mean? When you look at something and it looks blue, why does it look blue? Why does it look red? Whatever. So hopefully this diagram will kind of go some way to explaining that. So this object below is blue. Now, why do you see it as blue? Well, it's because of this. So imagine this thing here is a light beam coming from the sun or any other source, but it's white light, visible light. Now, as you remember, or you've seen rainbows and so on, white light is composed of all these other different colours. We can remember all that stuff probably from school. So it's got all these various colours in it. It's a white light beam. It comes down and it hits this object. And basically what happens is that the blue portion of it, in this case, the blue portion does not get absorbed by the object. It gets reflected. So the white light comes in, the blue light gets reflected and eventually goes into your eye and you see it as blue. All the other colours either get absorbed by it if it's opaque, or transparent, or pass through if it's transparent. Okay, so that's why it looks blue to you. So if it was red, basically the white light comes in and only the red bit gets reflected into your eye. Okay, so that's what a colour is. So how does that relate to lasers? So let's go to the next page and hopefully this will explain it. So thinking about what we just said, let's think about this now as a laser. Now a laser isn't a white light. It's a very, very specific colour. So you can get blue lasers and all sorts of things, right? The one I've got is a blue diode laser. So this is the laser beam coming down here vertically in this case. Doesn't have to be vertically, but generally, of course, they are. So it comes down vertically. Now this is a blue light of a very high energy. So it comes down and it hits this object, which happens to be red in this case. So because it's not blue, this red absorbs the energy in this beam, and it gets hotter, locally. So you can imagine at the microscopic level, it's going to start to melt eventually, depending on the power of the laser, and effectively it's going to cut that material. And of course that depends on the amount of energy you put in through it, how thick this material is, and also its colour. So it gets hot. Blue light comes in, it absorbs because it's red, it's not blue. Look at this other example here. Blue light comes in, and because the object is blue, it doesn't get absorbed. It literally reflects it. So the light comes in and it just is completely reflected back. This blue here might as well be a mirror. It just gets reflected by the beam. Consequently, this object stays cool and does not get hot enough to cut. So theoretically, if the colour of the object that you're trying to cut is exactly the same colour as the laser beam, it won't cut. Okay, now it's a very crude example, but hopefully you can see the kind of thing that's going on. The reality is, of course, your blue laser, in our case, it isn't exactly one colour of blue. It's got a variation on it, so even blue will be able to cut. But if in the ideal world the material was exactly the same colour as the blue light, it wouldn't cut. Right, so let's go on to our little document and try and explain some of the other things that you get when you start looking at these things. Now this laser here, and this applies to all different types of laser, but the laser that I've got is a 20 watts, so-called 20 watt blue light laser. So this light beam here is blue. Now the important thing is, if you look at the specs of the laser you're going to buy, it's not really that easy to see, is it? Let's zoom in a bit. Okay, so this is what they quote, the people who sell this laser. It's a 15 watt laser. Well, that doesn't really matter at the moment, but we'll come on to that. They quote the laser wavelength. So the wavelength in nanometers, 10 to the minus 9, doesn't matter about that too much either. But the point is, the number is 445 plus and minus 5. So there's that tolerance again. Now, that 445, you can look at that. It's a wavelength of light. Now this chart here, each colour has got a certain wavelength associated with it. Now the wavelength of 445 is kind of in between these colours. It's round about a violet and blue. That's the sort of colours. And this is an energy thing. But so it's blue on the spectrum. Now the other important thing to look at here is that although this is classed as a 15 watt laser, it's almost a marketing thing with diode lasers. That's the power taken by your power supply effectively. What's important is not that number, it's the power at the beam itself, right? Now that's this one here. That's what they've called luminous power. In fact, they're not hiding anything. They say here, electrical power 15 watts, luminous power, and they've quoted it in milliwatts. So 4,000 milliwatts is 4 watts. So it's 4 to 4.5 watts, and this is a 15 watt version. CO2 lasers, which is another type of laser, they don't do it like this. They quote the actual power at the beam. Now typically you've got a 40 watt CO2 laser you can buy from eBay or these various sources, and they're 30 watts. So you can see that this laser I've got is much lower power. So the 15 watt is more of a, let's say, a sort of marketing ploy, if you like, but they all do it. Everybody who does diode lasers talks like that. So anyway, the important numbers to take from this is the wavelength of the light and the power. So it's 4.5 watts. I've got this version, the 20 watt version. It's the same wavelength, but it's slightly higher power. So it's 5 to 5.5 watts. Now let's just zoom out. So again, this is our color chart. This is our spectrum. Remember, rainbow spectrum. Now 445 is here. There's that, and that's the color that represents, which is blue. And we know it's blue because when you look, not that you should look at it, you can see the beam is clearly a blue color. Okay, and this is the visible spectrum. So we're up here And red, for example, is almost the opposite end of it. It's far, it's far away as it's possible. So notice the way, yeah, okay, we've covered that. So if we come on to now, let's look at safety, which is the whole point of this, and shielding and things like that. How does all that stuff work? Right. Well, first of all, this chart here, these lasers are potentially dangerous. All this information I've got from various sources. Okay, some of it relates to Europe, some of it relates to the States, but I mean, I figure it's all good stuff. So lasers are classed with various numbers, as you probably know. Class 1 laser is classed as non-hazardous. This is certainly European. I don't know whether it's international. I think it is international. We are using a class 4. This is what's called a class 4 laser. And for a class 4, it says, I'll read it if you can't see it. It says eye and skin hazard for direct and diffuse exposure. Diffuse exposure means the reflected beams. Fire and burn hazard, right? And then it says eye protection and other personal safety equipment is required. In other words, this is mandatory, really. Okay, so if you were operating this in a business, you must wear eye protection. Okay, these are very dangerous pieces of kit. This can absolutely blind you, no problem whatsoever, if you looked into the beam. We'll come on to that in a minute. Now, in Europe, a class 4 laser it says here, class 4 lasers must, and the word must means it's mandatory. Class 4 lasers must be equipped with a key switch and a safety interlock. In other words, if you operate like that, with this laser just plonked on your desk, in Europe, if you were in a business sense, that is completely illegal to do that. This thing has to be interlocked. In other words, you can't operate it without using a key switch, some sort of keyed switch. So plonking that on your desk is not legal in Europe, okay, for business. I mean, I suppose the logic is that you can do what you like in your own home, but this is saying, basically the takeaway is that this is a dangerous piece of equipment, and personally I don't operate mine without it being enclosed and wearing glasses. We'll come on to that. So that's for Europe. I'm sure the same thing applies in the States, to be honest. Now, some of this is related to America now. So this business about energy and light going into your eye. Say this beam shot in your eye. Any of these lasers, say they went into your eye because it reflected or whatever. Laser pointers, a big problem. This is what the American FDA talk about in terms of the maximum power that you're allowed to be zapped with in your eye before it starts to damage. And they quote a figure of 5 milliwatts. That's 5,000th of a watt into your eye. Okay. Now remember that our laser is not 5 milliwatts, it's 5 watts. So our laser diode has got 1,000 times more power than they quote here as the minimum allowable going into your, the maximum allowable going into your eye. So our laser is 1,000 times more powerful than that. In other words, if you fired that laser into your eye, it's game over. So to get down to this sort of level, you need to protect yourself, and you need to protect yourself by using glasses or some sort of enclosure, that type of thing. So how does that work? Well, laser glasses, for example, they quote what's called an OD number, optical density, I think it stands for. Anyway, it doesn't really matter, but they quote an OD number. And the number goes from 1, 2, 3, 4, 5, 6, etc. So what does all that stuff mean? And well, if we look at this chart here, the OD number basically tells you how much of the laser's energy the glasses, in this case, will absorb. So if an OD of 0, if you had OD of 0, it wouldn't absorb anything. It would let all the light transmit through. In other words, it'd be clear glass. So that's obviously not very good. OD1 is 10%, 2 is 1%, 3 is 0.1, and so on. So basically, the OD, you can think of that as the number of noughts that you need to divide by. So, for example, maybe I haven't made that clear. So, for example, if you've got a 20-watt diode laser, which actually is rated at 5.5 watts, that's 5,500 milliwatts. For an OD3 glasses, you basically divide that number by 1 with 3 noughts, i.e. 1,000. So if you divide that by 1,000, you get 5.5 milliwatts. If you protected yourself with OD3, 5.5 milliwatts. Now, unfortunately, 5.5 milliwatts is slightly over the 5 milliwatt allowable for the American FDA. So theoretically, if you just used OD3 glasses, they're not good enough. But that's, of course, if you get a direct strike from the laser, which hopefully you're not going to do. So OD3 probably isn't really good enough. Theoretically, it is for the 15 watt. I think that was just about 5. So that's what OD is. That's what it means. So let's look at some actual glasses. These are the ones I ended up buying, in fact. They're not cheap, but then again, £42, dollars. It's your eyesight, you know. Anyway, these glasses that you can buy, I got these off Amazon. They quote, and I think it's probably a legal requirement, they actually engrave on them the OD value and also, of course, the frequency, the wavelength of the lights that they work in, because that's important. You can't just say, oh, it's OD6, because you need to look at the wavelength as well. So these particular ones are OD6. And you can just about see they operate in 2 wavelengths. It says at the top end 532 nanometers, and I think this was the graph that for these glasses. So basically, OD6 is massively better than OD3. In fact, it's 1,000 times better. So these are more than up to the job of absorbing, and they absorb the light over this frequency range, which our laser, or my laser, is 450. So here I'm on that point of the graph, so it's OD6. Beyond 500, let's say 550, you can see the OD value, which is this thing here, the y-axis. The OD drops dramatically. They don't work basically between, let's call that 550 and 700. They just don't, they're not very good. They're about OD1, which you wouldn't want. But then they go up again. So they go up in a different, so for another frequency range. So if your laser is in, let's say, 900 to 1100, you're up here, which is again back in OD6. So it's got 2 ranges. So that's that. So these are going to work. Now, you get laser glasses when you buy your lasers. And I got some, and they probably work. But the problem is, for me personally, I think they hadn't got anything engraved on them. So you have no idea what OD value they are. So how do you know? You're gambling, aren't you, really? So I took the decision to spend 40 quid and buy a pair of proper rated glasses. Unless it's got that engraved, you're gambling a little bit. So while on the subject, shielding. Now this is really popular stuff. People sell acrylic sheet that's OD rated, and generally it seems to be just these people in America. Now I'm absolutely not against that. I think it's this company. I think it's brilliant what they've done actually. But let's look at that. Yeah, I think that's about the end of my document. Although there's a lot more to it actually, but it's more related to cutting. Oh, actually, I'll tell you what. I'll show you before we do that. I'll just show you. This is the setup I ended up doing, which is now in a black box. and I suck the fumes out like this and all the rest of it. Anyway, it works pretty well, but it's black opaque, and I still wear the glasses. I'll just show you very briefly a test I did with cutting. So here's our going back to our colour stuff again. So the colour is blue, so blue is not a good colour to cut. So what I actually did, we got lots of different colours of latex. So I figured that looking at the colour spectrum, we're here. So blue is going to be difficult to cut. So the further away you get from blue, it's going to get easier. So I figured that red would be easy to cut and probably black. So I put a few strips together and did passes straight through them, and sure enough, that's exactly what you saw. The red and black colours cut in one pass, literally just sliced through them. All the other colours took multiple passes, and the blues took longer. They did cut eventually, and the reason they cut is because of course they're never going to be the exact same colour as your laser, and your laser's got a tolerance anyway, so they will cut. They just take a lot more effort. So that absolutely proved what I was sort of saying. Finally, going on to the laser shielding stuff. So this company here sell laser, in inverted commas, sheeting, and the questions have been asked, well, is it some sort of fancy special acrylic, it's got some kind of magic Harry Potter properties built into it? Well, no, it hasn't. It's just acrylic sheeting. However, what they have done is that they've chosen a colour. In this case, it's orange, which happens to be very similar to the colour of my glasses. And what these people have done, which is brilliant, is they have tested it. Okay, so you can imagine, you can't just pick some orange sheeting and say, oh, that'll do. Well, you could, but you can't tell me if that's OD 1, 2, 3, 4, what is it? These people have actually done the tests. Now, that is not going to be cheap, I can tell you. It's called laser spectroscopy, is what you do. And actually, this is a good little diagram. What they actually do to test this is you fire a laser at the object, in this case your perspex, and you basically measure the amount of energy that comes out, the amount of energy that's absorbed, and from that you can work out what the OD value is. So this basically costs money. Obviously, I bet they've spent a lot of money to get that tested. It wouldn't be cheap. So they're selling this at $34 for a 2 foot, is it, somewhere? I can't remember now. Yeah, 2 foot by 1 foot in old school. So you kind of think, well, why can't I just buy some orange stuff off the internet? Well, you could. For example, here's an example here. Now, this company, I think they're in the UK. Yeah, they are in the UK. So they sell orange acrylic sheeting of exactly the same thickness. And for the same size, 600 by 300, it works out at £7 for that sheet. Now, if you just look at the difference here. So this is the American company that have done the OD rating, $34. And here's the UK off-the-shelf building company or whatever, and they're charging £8, roughly the same thing. So there's a 4 times difference. So this OD stuff by these people is 4 times the price of this. So why don't you just buy this? Well, the reason you don't necessarily buy this is you have no idea what the OD rating is of that. And there's the difference. It may well work. It probably will work, but I'm not telling you that because I don't know. And without testing this, you won't know. So by buying something that looks the same, it'll possibly work, but you don't know. So I think if I was purchasing, I still would go and buy this stuff from this because they've done the test. Now, we've already seen, of course, that OD3 isn't really good enough anyway. But, of course, that's looking at a direct strike. You're not going to look at it directly, are you? You've got OD3 coming through this sheet here. So if you fired that laser directly at this sheet, then it'd be just about on the limit of acceptability according to the American FDA. But the reality is you're firing the beam directly at the object. The only light that's coming back is reflected light, which is a much lower power. So this sheeting is probably more than up to the job on its own. But me personally, I wear those glasses, and they're OD6, and they're way better than this sheeting. So if you had a box, and you see some of the guys online, if you've got a box where you've got this sheeting over it, and you wear glasses as well, you're well protected. Absolutely well protected. So, yes, you can buy cheaper stuff, a lot cheaper, 4 times cheaper. But you don't know what that's going to do. Now, you could probably test it yourself with your own laser, try and burn something underneath, but ultimately you don't know the amount of energy that's coming through, than the amount of energy that's absorbed by this thing. So it's a gamble. It's a gamble. But bottom line, I suppose, with all of this stuff is just don't look into the beam. Never, ever look into the beam directly. A bit like Ghostbusters, right? Don't cross the streams. Don't look into the beam. And you're going to be fine, aren't you? Wear some glasses. Treat it like a very dangerous power tool. And it's a lot more dangerous than a power tool in a way, isn't it? Because a circular saw, if a circular saw, you got your arm in the way, let's say, and it started to cut you, very quickly you would pull your arm out of the way, wouldn't you? And you'd shut the saw off. And yes, you would injure yourself, and potentially quite badly, but you could react, and you would react relatively quickly, in milliseconds, and you'd pull your arm away and you'd cut yourself, etc. But with a laser, it's instantaneous. As soon as you see that beam, that's it. You can't pull away. You can't blink fast enough. It's game over. So treat it with the utmost respect, and you'll be fine. I would say, in closing, certainly consider some sort of enclosure. I must admit, I personally don't like seeing these things plunked directly on desks because, well, I mean, there's safety built in, isn't there? If they tip over, they're supposed to switch off. But I mean, if that reflected off something and went in your eye, it's game over. So, sound like that guy from Aliens, don't I? Game over, man. Anyway, there you go. That was not really a quick video, was it? Hope it was some use. If there's stuff I've missed, stuff I've got wrong, let me know. Absolutely, let me know, 100%, and I'll change it, because it's all about education, isn't it? And I'm happy to learn as well. All right, have a good day, and maybe speak to you soon. Thanks, guys and gals. Bye.